Okay, good morning, everybody, and welcome to the Book of the Dead, Optimizing Performance for High-End Consoles. My name's Rob Thompson. I'm a console graphics programmer here at Unity Technologies, and my primary responsibility is PlayStation 4 graphics. So this presentation is a technical presentation focused primarily on graphics optimization, and we're going to be looking specifically at Xbox One and PlayStation 4. Now, graphics optimization for these consoles is a massive topic. We can only really scratch the surface in the 45 minutes we have available to us. We're going to try and give you some salient points for what you, as Unity developers, can do to make your experience developing for these platforms a better one. Specifically, we're going to do this by looking at a case study of the optimization of a project based on scriptable render pipelines. Now, if you don't know what SRP is, very quickly, SRP is a new feature to Unity this year that allows you to code the core of your render loop in C#. And consequently, it gives you much more flexibility for customizing how your scene is drawn to make it specific to your content. But as an additional consequence of that, it also gives you much more scope for making optimization decisions within your graphics pipeline than you've ever had before with Unity's built-in renderers. So some background first about the Book of the Dead. So the Book of the Dead was a real-time rendered animated short that was released at the start of this year to critical acclaim. It was essentially produced as a showcase for the capabilities of high-definition render pipeline, or HDRP, as it's known. And HDRP is one of Unity's template scriptable render pipelines. It comes with all of the features that you'd expect from a modern AAA quality, high-fidelity renderer. And the Book of the Dead was put together as a showcase for that to show off its capabilities. If you've not seen it in full, you can find it linked off our website. The Book of the Dead was produced by Unity's demo team, who have previously brought you demo pieces such as The Blacksmith and the first installment of the Adam series. So we'll just take a quick look then at some snippets from that original real-time rendered short.
You spent nearly 90 years there.
What? No. No, not there. The forest is just the lobby. That's where the entrance is.
Your brain is now remembering things that never happened to you. Or to it.
Sorry.
Are you all right?
Yes, I'm just tired.
Okay, so what we can see that we've got there is a lushly rendered, rich forest environment. And that made an excellent showcase for the capabilities of HDRP. What the demo team wanted to do next was to create an interactive experience where people could wander around inside that environment and get their hands on it and experience it in a way that was familiar from a traditional AAA games perspective. So specifically, the objectives for this interactive Book of the Dead demo was to allow people to explore the environment using a standard console controller, to show that we could hit very high-quality rendering on the kind of hardware that people already have at home underneath their TVs, and that this wasn't a requirement to use HDRP with some massive, titanic, high-end spec PC. Specifically, we wanted to show this running on Xbox One and PlayStation 4, and we had the performance requirement that it hit 1080p at 30 frames a second or better on a PlayStation 4 Pro or on an Xbox One X. And we also wanted to use this as an example for how to use HDRP on consoles. I think, as was mentioned yesterday during the keynote and other presentations, all of the assets and all of the script code for this interactive demo are now available for you to look at and interrogate via the Assets Store. So what we're seeing here, juddering aside, is a stream that comes directly from the PlayStation 4. So this is that same environment running in HDRP in real time on a PlayStation 4. And this was recorded and used originally at the GDC keynote earlier this year that was presented by our rendering leads. If you're interested in experiencing this demo for yourself, you can see it during the conference at the Sony and Microsoft booths. And specifically, this is the scene that we're going to be talking about the optimization of for the rest of this presentation. Okay, let's move on then, and let's have a look at what we did to optimize that particular environment. Okay, so the first thing we did was we found a sample scene that gave us the worst case performance throughout that environment. Now, the Book of the Dead, it's fairly straightforward what's going on in each individual scene. We haven't got any unusual parts where suddenly we get thousands of particles spawning into life or suddenly loads and loads of animated characters appearing. What's going on in the scene is pretty much constant. What's a variable is what's within the view of the camera. So once we'd found a view that was consistently giving us the worst performance, then we knew that was the one that we needed to optimize, and that if we made savings here, we'd be increasing the performance throughout the entire demo. This view that we're looking at here was consistently the worst. And the reason why this was the worst is essentially it's an exterior view of the level looking into the center of it. So the vast majority of stuff in the scene is in the camera frustum from this view. There's a lot of draw calls here. And so this was basically the scene that we used as our optimization template, essentially. Bit of a summary about what we're looking at here. So this is a deferred rendered scene using HDRP, as I mentioned. Most of the artist-authored textures are between 1 and 2K size maps. There's a handful at 4K. We're using baked occlusion and baked GI for our indirect lighting. And we're using a single dynamic shadow casting light source for our direct lighting from the sun. Typically, we're issuing around 2,000 draw calls in any point in this demo, give or take a few hundred, depending on where we are in the scene. And when we started our optimization pass, this view was GPU bound on PS4 Pro at around 45 milliseconds. Now, I'm going to talk first about CPU performance. And this actually really wasn't a big headache for us in this demo. That's because this isn't a full game. We haven't got the complexities of the script code that goes along with all of the systems that's necessary for a full game. All we're concerned about in this demo is primarily rendering work. So this wasn't a massive issue for us in this particular case. But there's a few things that I want to say to call out to you now that will hopefully be of use when you're developing on these platforms. So the fundamentals to keeping rendering work cheap on the CPU is by controlling the batch count. The more stuff you draw, the more expensive it's going to be for you on the CPU. So using mechanisms that keep your batch count under control are crucial. This view, we need 1,832 batches, or individual draw calls, to render this scene. And that's not really that many when you consider the complexity of what's going on here. We've got all these individual blades of grass, we've got lots of rocks, lots of scattered twigs and stuff on the ground, and that's before we get to the undergrowth and the trees and all the rest of it. So the demo team were able to keep the batch count low through a use of occlusion culling, which was covered by Julian during his talk yesterday on how the art was created for this scene, but primarily through the use of GPU instancing. Now, this is really crucial to keeping your batch count under control in complex scenes on console. Now, that may seem obvious to the more experienced of you, but the number of PlayStation games I've profiled on Unity where that has not been used and could have been used is really quite large. So it seems worth me re-emphasizing that point. Dynamic batching, which is typically used on mobile platforms to keep the batch count under control, is seldom an optimization on console hardware. So don't rely on that saving you CPU performance. Try it by all means, but don't bank on it. GPU instancing is a much better win. So just to emphasize that point, without GPU instancing, we'd need 4,500 batches to render this particular view. And while we could handle 4,500 batches on PlayStation 4 Pro, particularly if we're using native graphics jobs, which I'll talk a bit more about shortly, the key thing to note here is through intelligent use of instancing, we've reduced the number of draw calls being issued by a factor of 100%. So bear that in mind. Also, don't assume that using GPU instancing is going to create repetitive, samey-looking scenes. I think it was shown in the keynote last night that the number of individual assets that were used to create this scene is actually very small. Through good quality assets and placing them intelligently, you can create complex scenes that don't look repetitive and with a low batch count through the use of GPU instancing. Here's a scene with no instancing. So you can see just how much of the scene is drawn in that way. There's the original again, and there we are again with no instances. So that's a key takeaway, really. So I'm going to talk next about graphics jobs. So both the Xbox One and PlayStation 4 are multi-core devices. That is that their CPUs have multiple cores, and in order to get the best CPU performance, we need to try and keep those cores busy all of the time. In Unity's runtime, all of your script code ends up in what's known as the main thread. And the main thread on these devices has a single CPU core dedicated to it. To not make that the bottleneck, we need to try and get as much work as we possibly can away from that main thread. And graphics jobs is Unity's mechanism for doing that. Sadly, it is not enabled by default on console, and it is still flagged as experimental. Now, the reason for that is that some of Unity's internal profiling tools don't work correctly when graphics jobs are enabled. And that's in the process of being addressed. But that isn't an issue for us on console because we have the platform holders tools to use instead. And I'll cover those in a bit more detail subsequently. So graphics jobs will get you a performance optimization in almost all circumstances on console, unless you're only literally drawing a handful of batches. You can find them in player settings, other settings, as described here, and they come in two flavors. So we have legacy jobs, as it's described. Legacy jobs is available on DirectX 11 for Xbox One. And we have native jobs, which is available under DirectX 12 for Xbox One, which is coming soon. We have both options available to us on PlayStation 4. So what do these do? Well, legacy jobs does a good job of taking work off that main thread, which is the crucial part. But in very large scenes, it can create its own bottleneck on what's known as the render thread. And this is a thread that Unity uses to talk to the platform holder's graphics API. So it can create its own bottleneck, but generally it will still be a win for you over having no jobs on at all. Native graphics jobs, on the other hand, does the best job of distributing all of the rendering work across all of the available CPU cores. Unfortunately, though, in Unity 18.1 and earlier, in some scenarios, it could end up leaving more work on the main thread than legacy jobs does. Now, that side effect has been cured in Unity 2018.2 and onwards. So on platforms where you have native jobs available, this is the one that I would generally recommend you go for. But it's worth doing some experimentation with your own particular use cases to see which one will get you the best optimization scenarios. OK, so we're going to look at the GPU now, and this is where the real nitty-gritty of optimizing this demo came in. So first, let's talk about the platform holders' tools. So we're particularly blessed on console that the platform holders provide us with absolutely excellent tools for analyzing our performance both on the CPU and on the GPU. These tools are available to you for free if you're working on console. Learn them and use them. They are absolutely critical. Pix for Xbox One is Microsoft's offering, and the Razer suite is Sony's offering. And really, they are your main tool in your arsenal when it comes to optimization on these consoles. All of the information that I'm presenting in terms of timing and all of the analysis that was done on PlayStation for optimization of this demo was done in Razer. And another word to the wise. Get onto console development early in your dev cycle. Don't wait until a week before your first console milestone or deliverable to try your first Xbox One or PlayStation build. Because if you do that, you will typically get a nasty surprise at the performance characteristics of these devices in comparison to your average development desktop PC. Also, getting onto console dev early gives you the most opportunity to get the best out of these tools, which are really very good, and in my opinion, much better than most of the stuff that's out there for desktop. So let's break down our GPU frame now, step by step, and see where we were at the start of this optimization process. So we're deferred rendering. So the first thing that we're going to do is create a Gbuffer. We have 4 MRTs bound and our depth target. If you're interested in the Gbuffer layout, you can find a description of the Gbuffer layout for HDRP in a Unity blog post made by Sebastian Lagarde, and you'll find that on our website. To start with, our Gbuffer was taking us 11 milliseconds. Then we render some motion vectors and some screen space ambient occlusion information. That's pretty swift. Then we render our shadow maps from our directional shadow casting dynamic lights. We have 4 shadow map splits, and initially this was coming in at a whopping 13.9 milliseconds. Then we move on to do some deferred lighting at 4.9 milliseconds. And then some atmospheric scattering. Right, I'm going to pause and talk about this effect just a little bit. So atmospheric scattering is the effect that produces those very dramatic shafts of light, or God rays as they're often referred to, that you see as the light swings through the trees in the demo. It adds a lot of bang for buck. It's very dramatic. It's key to the kind of atmospheric nature of this scene. The atmospheric scattering implementation that was used by the demo team in this demo is not the one that you will find in vanilla HDRP. The reason for that was that the atmospheric scattering in HDRP was still in the infancy of its development at the point this demonstration was put together. And the demo team already had an atmospheric scattering effect that they'd written for the blacksmith. So they took that effect and they customized their scriptable render pipeline to use that. So this is a really good example of customizing the template that Unity provides for you to add an effect that's specific to your game or to your title and that suits your needs better. Curious about looking at it and using it. Initially, this was coming in at 6.6 milliseconds. And then finally, we have some temporal anti-aliasing and some post-process, which came in at 7.6. So this is our GPU frame laid out from start to finish. As you can see, we're at 45 milliseconds, and the 2 vertical orange lines show where we need to be to hit 30 frames a second and 60 frames a second, respectively. Now, my eye as a graphics programmer, when I look at this, is let's look at those big sections. Let's see if we can reduce the bigger chunks of this down to make those more efficient. So we're looking at the Gbuffer pass, the shadow maps, very, very much so. That atmospheric scattering pass to me seems quite expensive at 6.6 milliseconds. And then we've got our post-process at 7.4. Now, we didn't do much with post, so I'm just going to speak about that quickly now. When it comes to optimizing post-process, it's seldom a desperately technical process. Normally, in Unity, optimizing post-process is a question of turning stuff off or turning dials down or up for what the visual quality is. So my advice to you when it comes to post-process is put your post-process on, find out how long it's taking you on the GPU, iterate over it until you've got the right visual quality versus time trade-off for your post-process, and then leave it alone, because it's going to be a static cost pretty much in every scene. And then you know what the rest of your GPU budget is to spend. The really crucial part of that, though, is know how much this is costing you. I've profiled Unity games on PlayStation 4 where literally 2/3 of the frame were taken up by post-process, and the developers didn't realize that that was the case. And often that comes about by downloading asset store assets that are post-processing that have been authored primarily for PC. They appear to run fine on console, but actually the performance characteristics are really bad. So be aware of what this is costing you. OK, let's look at our Gbuffer next. OK, so when we first looked at this, the first thing that sprung out to me was that we're using tessellation in our Gbuffer and in parts of our shadow mapping pass. And this is not something that I would recommend people do on console if you can avoid it. Generally speaking, you are a lot better off using the equivalent artist-authored assets than you are runtime tessellating them on the GPU. And that would be my advice. There needs to be a really good use case, something that you're doing in tessellation that you can't achieve in offline artwork to justify using it, in my opinion. So why are the demo team using it here? Well, it's tree bark. Tree bark is a pretty much ideal use case for tessellated displacement. Tessellated displacement allows us to add these kind of deep recesses and gnarly details into the geometry that will self-shadow correctly in a way that normal mapping won't. And these trees are kind of the hero objects of our scene. When people are navigating this environment, typically it's the trees that they're looking at and going, ooh, doesn't that look pretty? So because those are the things that people are looking at, it's a justifiable decision to use more of our GPU resources in rendering those hero objects. And this is a case where this decision was justified. Specifically, this was done by, we have the same mesh used for our trees at LOD 0 and at LOD 1. And the difference between them is simply that we're scaling back that tessellated displacement so that it's no longer in effect by the time we reach LOD 1. This also means we get very smooth LOD transitions on the trees, which was crucial for the visual look of the game. So we decided to stick with tessellation on these trees, even though we knew it was causing us some performance worries. So let's analyze a bit more now as to what was going on with our Gbuffer performance. So this is where we get slightly more hardcore. So let's talk about wavefront occupancy. Okay, what's a wavefront? Well, you can think of a wavefront as a packet of GPU work. When we submit a draw call to the GPU, or a compute shader dispatch, then that work is split into many wavefronts. Those wavefronts are distributed throughout all of the SIMDs within all of the compute units that are available on the GPU. Each SIMD has a maximum number of wavefronts that can be running at any one time. And therefore, we have a maximum total number of wavefronts that can be running in parallel on the GPU at any one point. How many of those wavefronts we are using is referred to as wavefront occupancy. And this is a good metric for how well we are using the GPU's potential for parallelism. And parallelism is what makes GPUs fast. So we want to try and be getting good wavefront occupancy at all times on our GPU. And Pix and Razer can show us this in great detail. These graphs that we're looking at here are screenshots from Microsoft's Pix for Xbox One tool. On the left, we have an example of good wavefront occupancy. Along the bottom on the green strip, we can see some vertex shader wavefronts running. And above that in blue, we can see some pixel shader wavefronts running. So what's happening here is we're getting our vertex shader work, we're transforming our vertices, we're getting lots of pixels rasterized, we're spawning pixel shader wavefronts to shade them, and that's all great. On the right, though, we can see that that's not happening. What we've got here is a lot of vertex shader work that's not resulting in much pixel shader activity. We're not seeing very many pixel shader wavefronts used. And so this is an underutilization of the GPU's potential. How does this come about? Well, this scenario is typical when we're doing vertex shader work that doesn't result in pixels. So if we're rendering stuff off screen, for example, or if we're rendering stuff that's failing the depth test, or if we're rendering loads of back faces, or we're doing some other work that means that we're not getting pixels as a result of our vertex shader transformations. And in our particular case, this was down to overdraw. So some more analysis in Pix and Razer showed that we were getting a lot of overdraw during our Gbuffer pass. And this is particularly bad on console when we're looking at alpha-tested objects. On console, if we're issuing pixel discard instructions, or if we're writing directly to depth in our pixel shader, we can't take advantage of early depth rejection. So those pixel shader wavefronts get run anyway, even though the work is going to be thrown out at the end. So the solution here for us was to add a depth prepass. A depth prepass is where we render the whole scene in advance to depth only using very light shaders, and that then can be the basis of more intelligent depth rejection when we've got our heavier Gbuffer shaders bound. HDRP now includes a depth prepass for all alpha-tested objects, but you can also switch on a full depth prepass if you want. And the settings for controlling HDRP and what render passes are used and what features are enabled are all made available via the HD render pipeline asset. So if you search in a HDRP project for the HD render pipeline asset, you'll find a great big swathe of checkboxes that control everything that HDRP is doing. There's a section of it on the top right there that shows where the depth prepass option can be found. For us, this was a great GPU win, but it does have the overhead of adding more batches to be drawn onto the CPU. So you do have to be careful there as a trade-off between GPU and CPU performance. Now, as I mentioned earlier, we had CPU performance to spare here, so this was a win for us, but your mileage may vary. So also during this phase, we did some asset optimization. We made sure our LODs were appropriate sizes and set at the right distances. We also did some internal engine work to improve the performance of tessellation. So this is a good example about how when Unity does this kind of demo, it also indirectly benefits you by allowing us to find bugs before you find them. So after this pass was completed, we had gone from a Gbuffer pass that was taking 11 milliseconds on the GPU to a depth pre-pass and Gbuffer pass that was only taking 6 milliseconds. So this is where we were after that initial Gbuffer optimization phase. We're creeping closer to that 30 FPS barrier, but we're not there yet. So now let's turn our attention to shadow maps. So as I mentioned earlier, our shadow maps are being generated against a single shadow casting directional light. We use 4 shadow map splits. And initially, we were rendering to a 4K shadow map at 32-bit depth. And this is the default for HDRP projects. Now, when rendering to shadow maps, the resolution of the shadow map is almost always the limiting factor here. And analysis and Pix and Razor back this up. So reducing the resolution of that shadow map seemed like the obvious solution. Obviously, it was going to have a potential impact on quality. But there were a number of other factors that were pointing that this was definitely the way to go. One thing that I want to call out before we move on is that we found that there was an interesting install. Well, consoles write to compress targets, and that makes writing to those depth targets and depth faster. But before those depth targets can be bound as texture, and the bigger our target, the longer that stall is. Ammunition for us needing to reduce the size of our shadow mapping render targets. This can be a problem, depth decompression can be a problem for custom effects where you might be writing to some large depth atlas, say, and only updating it sporadically. Custom depth effects, this might prove a win for you. If you can see the script call for it at the bottom there, but just be careful as to how that changes the performance of rendering to that target in the first place. So the other thing to consider about the size of our shadow maps is that our shadow maps are consumed as inputs into various other places in the GPU pipeline. So when we profiled our atmospheric scattering pass, that takes many samples from our shadow maps, and we found that actually we were bound on bandwidth reading from those large shadow maps in our atmospheric scattering pass. So a large chunk of our time there was also going as a result of the resolution of these assets. So we dropped the shadow map resolution to 3K, and we found that this gave us a perfectly acceptable trade-off against performance. If you're interested in where you can control that in HDRP, again, it's on the HD render pipeline assets. You can see the blue arrow at the bottom is pointing to where it is, and I've enlarged that a bit there so you can see we've set it to 3K. But the demo team also added an option specifically to allow you to render to 16-bit depth shadow maps, and that's not available in vanilla HDRP. If you're interested in that and want to give that a go for yourself, download the Book of the Dead assets. The implementation's all there for you to use 16-bit depth shadow maps. And we found the quality of this was fine for our scene. If you're going to change the resolution of your shadow map, you also need to change some settings on the light that are writing to it. There's a setting that shows what resolution each individual split will be rendered at that I've called out here. So we needed to set that to a quarter of the size of our new depth target resolution. Okay, so we've made our shadow map revisions, and we've repositioned our shadow mapping camera to try and get the best utilization out of the new reduced resolution we have in our shadow maps. And at this point, the demo team came up with a really clever little optimization. So we only draw the most zoomed out shadow map split once at level load. Now, our shadow mapping camera doesn't move about much, so we can get away with this. That most zoomed out split is typically used for rendering the shadows that are furthest from the player camera's eye. So we didn't see a drop in quality as a result of this, and it was a really good optimization because it saves us both GPU time and it reduces batches on the CPU. And if you remember, we'd already added some more batches from our depth prepass. So by doing this, we've clawed some of those batches back, as well as saving ourselves some GPU time. The demo team also experimented with only updating the second and third shadow mapping splits on alternative frames. And this also was a really good optimization, but because of the nature of the wind in the Book of the Dead, there's a very chaotic wind blowing around these very tall trees. Actually, it kind of gave the effect that the shadows were running in slow motion. So we backed away from that one, but all the code to do that is still in the assets that you can download if you're interested in trying it out for yourselves. So after all this was done, our shadow map creation phase went from 13 milliseconds to just under 8. And also our lighting pass went from 4.9 milliseconds to 4.4, and our atmospherics pass went from 6.6 milliseconds to 4.2. And this is where we were at the end of that shadow mapping optimization. So we're now within the boundary where we can run at 30 frames a second on PlayStation 4 Pro. Hooray, my work is done and I can go home. So this is kind of where we left it at the end of our optimization pass. And the demo was subsequently iterated on to add more rendering systems and more content. So when you download the stuff from the asset store, it won't line up with these graphs. But it's still under 30 FPS on PlayStation 4. And that's really kind of the example of an optimization pass on console to get us within frame. So we've saved ourselves in the region of 15 milliseconds through those optimizations with no visible drop in quality. So there's one other topic that I want to call out before we wrap this session up, and that's async compute. Okay, so what is async compute? Well, async compute is a method for us to utilize periods of underutilization on the GPU with useful compute shader work. So let's imagine some fictitious rendering situation where here we've got a diagram, a mocked-up diagram of wavefronts running on a single SIMD within our GPU. First off, we're doing some traditional vertex and pixel shader rendering. So on the left-hand side, you can see we've got some green vertex shader wavefronts running, and we've got some blue pixel shader wavefronts running, and we've got great wavefront occupancy on the SIMD there. Then we do some depth-only rendering. We've not got great wavefront occupancy during that pass, and I'll come back to that in a minute. Then we're doing some compute shader work. That's the yellow wavefronts that you can see there. And then finally, we go back to doing some traditional rendering again. Now, during depth-only rendering, we typically see an underutilization in the GPU. And this is the situation because on console, we don't even need a pixel shader bound to be able to write to depth. So we've got all of those wavefronts going spare. And even when we are using pixel shaders in a depth-only pass, typically we're not using much in the way of computation. So the depth-only phase, which is what we're doing with shadow mapping, is traditionally a point where we're not making full use of the GPU's potential. Now, wouldn't it be great if we could move all of those compute shader wavefronts into these gaps, thus making better utilization of the GPU? And that's exactly what async compute allows us to do. It allows us to move our compute shader work to run in parallel with our graphics queue, making use of resources that the graphics queue is underutilizing. In this particular scenario, our depth rendering is making very little use of computation, whereas this particular fictitious compute shader work is very much doing computation. It's ALU bound. We're not doing much in the way of bandwidth here. So these two operations have totally different bottlenecks, and they make them ideal candidates to overlap. So that's what happens when we now run our compute shader dispatch on async compute, synchronized to run doing our depth-only pass. Our depth-only pass actually gets a little bit longer as a result, but we pretty much hide the entirety of that compute shader work behind it. So that's a really good optimization. The Book of the Dead uses async compute for its tiled light list gather, which is part of the deferred lighting that's all done pretty much in compute shaders on console in HDRP. and it also uses it for its SSAO calculations. Both of these overlap with our shadow map rendering to fill in the gaps in our wavefront utilization. Currently, in Unity, Async Compute is only supported on PlayStation 4, but it will be coming to DX12 for Xbox One very soon. And it's accessible through Unity's command buffer interface. It's not just exclusively for SRP, but it is primarily aimed at it. If you want code examples, download the Book of the Dead assets, or look at the HDRP source. I'm going to run you through some conceptual code for how we use it right now. So, what's going on in this pseudocode example? This is a kind of scriptable render loop style approach. So at the very top, we get a rendering command buffer, and we're getting that from a pool of rendering command buffers that we've already created up front. We're not newing that every frame, because that's going to result in GC allocs. So instead, we're getting that from a pre-existing pool. And then we're setting up some camera information, and we're doing some culling and issuing some rendering commands, perhaps for our Gbuffer or maybe for our depth prepass. And then we get to a point where we want to start issuing our async compute work. So what we do is we create a GPU fence. A GPU fence is something that says, it's a flag that we can essentially use to say, OK, hey, start my async compute work now. It's used for synchronization between our graphics queue and our async compute queues. So once we've created our GPU fence, then we execute all of the rendering commands that we've set up so far in that command buffer. Now, internally, Unity takes a copy of all those commands that we've created at the point where we call execute. So we're then safe to clear that command buffer and reuse it subsequently in our script code. Now, Unity won't kick all that stuff off to the GPU straight away. By calling execute, we're saying, OK, these commands are done with. Send these to the GPU when you're good and ready. So then we get another command buffer, and into that we put our async compute work, which is going to be some compute shader dispatches. And then at the end of that, once we've added all of our compute shader dispatches, whatever else we're doing on async compute, into that command buffer, then we create another fence. And this fence is used to say, OK, right, I'm done with my async compute work now. Anything that's dependent on this is good to go. So we add that fence. Then we execute our async compute command buffer, and then we return that async compute command buffer back to our pool to be used in other situations. Then we return to the graphics queue, and we render our shadows. So this means that our async compute work and our shadowing work will be scheduled at the same time on the GPU. And once we've finished our shadowing work, we then decide, actually, whatever it is that we're going to do next in our graphics queue, that's the point where we need to wait for our async compute stuff to be complete. So we wait on our fence that we created in the async compute command buffer. Then we do the rest of our GPU work, whatever that might be, our post-process or our other shadow rendering passes. And then at the end, we send that work off to be executed, and we return our command buffer to the pool. So that's basically a kind of high-level overview of the kind of workflow that you need to set up if you're using async compute. And you can find examples of that in the Book of the Dead and HDRP source, as I mentioned a few moments ago. So async compute can also be used with Unity's inbuilt renderers. You can attach async compute command buffers to lights and camera events, should you wish to. Right. So there we go. So let's look at the things that we've sort of discussed during this presentation. Let's wrap up and highlight a few key takeaways, basically, for this. So first and foremost, learn the platform holder's tools. Pix and Razor are very much your friends. Take the time to learn them. It will pay dividends in the long run. Get onto console early in your dev cycle. Don't get nasty surprises as a result of the performance characteristics of these devices, and get the most out of these excellent tools that you're basically getting for free. Use graphics jobs if you are on console, and experiment with which version will get you the best optimizations for your scene, and use GPU instancing wherever possible. Don't use tessellation without good cause. If you're writing your own script or render pipeline, even if it's a deferred renderer, consider a depth prepass. And be careful with your shadow mapping resolution. Remember, HDRP defaults your shadow map size to 4K and its bit depth to 32 bits. You may not need that much on console. Try enabling async compute if you're using HDRP on PlayStation 4. And if you're writing your own custom compute shader effects or work, consider using Async Compute for that as well. And if you're interested in how all this work was done, download the Book of the Dead assets from the asset store, interrogate it, mess around with it, and have a look at what's been done there and learn from it. OK, so I'd like to thank these people who helped with the preparation of these slides. And thank you very much for your attendance.